Imagine a completely lifeless world. It's at a state of equilibrium, but that equilibrium is unstable. For a slight displacement from it will begin a set of trajectories which further deviate from that state. As they do, some might terminate while others can survive. But what do we mean by survive? Well, if we label some states of a system as living and some other states as non-living, then survival simply means closure under the subset of states we consider living. Thus, we find that survival also sits in exact correspondence with the concept of stability. Think of a disturbance acting on the set of states representing a living organism. If the result of this disturbance keeps the states within the living subset, we say the organism has survived. The same applies if the states are vectors. Thus, survival is really about keeping certain essential variables within assigned physiological limits. In other words, the achievement of homeostasis. Organisms tend to be good at surviving. The reason is that they have developed regulators for shielding their essential variables from various disturbances. If the disturbance is a source of entropy, then this regulator, through the environment, is capable of blocking the flow of entropy from disturbance to essential variable. If we plot an essential variable with time, having a good regulator would look something like this, while having a bad one would look something like this. The variable could be the position, temperature, angular momentum, pH, whatever. What is important is that the set of permissible values has a smaller entropy than the set of all possible values. Let's now introduce a slightly different way of looking at the problem. Say we have a disturbance D and a regulator R, which both feed into the environment T, which in turn exerts its effect on E, while R acts based on information from D. We can represent this environment as a table with the possible values of D, R, and of the outcomes corresponding to the D and R combinations. This set of outcomes represents E. Let's now ask whether it is possible for the regulator to always force a certain outcome given the value of the disturbance. Say D chooses C. Then if R chooses B, it can make the outcome D. If D chooses A, it can make it go to D by choosing C. In fact, R can always win if it behaves according to the transformation shown here. But the situation might not always be so favorable to R. Different tables can have different number of rows, columns, or different outcomes, and thus different constraints. For example, if we have the following table and the target was D, R cannot always win. And if the target was A, R can in fact never win. Now consider a table where no column contains a repeated outcome, so that any change of this move must require a change in R's. In that case, we can see that the variety of distinguishable outcomes that R has selected cannot be less than the variety in these moves divided by the variety in R's moves. Thus, if R is unvarying, the variety in the outcomes will be as large as the variety in these moves. If R has 2 moves, the variety in the outcomes can be reduced to a half. If R has 3 moves, it can be reduced to a third, and so on. Generally, if we want to reduce the variety in the outcomes due to D, we would require a corresponding increase in the variety of R. Expressed logarithmically in terms of entropies, this means that the entropy of E cannot be less than the entropy of D minus the entropy of R. This is Ashby's law of requisite variety. It is undoubtedly the most profound law of cybernetics. To prove it, we first point out that the condition that no column shall contain a repeated outcome here corresponds to the condition that if R is fixed or given, the entropy of E cannot be less than that of D. Now, by algebraic necessity, the entropies are related by the following equation, for both sides are equal to the entropy of R and D. Also by algebraic necessity, the entropy of R and E cannot exceed the sum of the entropies of R and E individually. Now, if we substitute HR of D with HR of E in the second expression, combine the result with the third expression, and solve for H of E, we obtain the following inequality. If R is a determinate function of D, i.e. if HD of R is equal to 0, we arrive at the original theorem. What this theorem really teaches us is that if we measure the amount of regulation exerted by the reduction in the entropy of the essential variables, then the capacity of R as a regulator cannot exceed its capacity as a communication channel. This is a really remarkable discovery. In Shannon's theory of communication, the disturbance corresponds to the noise, and the regulator corresponds to the correction channel. Thus, the use of a correction channel to suppress noise and the use of a regulator to achieve homeostasis are homologous. Now suppose that the selection as to which outcome should be the target is done by a different system, C, which we call the controller. In that case, complete control over the outcome by C requires perfect regulation by R. In other words, the outcome must be a message of entropy 0, for C has chosen a single target. Of course, this doesn't prevent any of the components to be vectors, either as multivariable systems or as single variables at multiple instances of time, such as a sequence of disturbances invoking a sequence of regulatory responses. The regulation then is complex. Now suppose that the information about the disturbance is not obtained by R directly from D, but that R gets it indirectly through T, or perhaps even E. In that case, we have the basic form of the servo mechanism. A servo mechanism is a device which uses error-controlled negative feedback to correct the action of a mechanism. If the variables are numerical quantities and the controller provides an input I, which is passed by T to produce an output O at the essential variable, we can define a transfer function for T which relates the output to the input. Now, if we want to make the output match this input, we can have the regulator modify the original input before it's passed to T. Assuming unity feedback, this modified error signal will simply be the difference between the target output set by the input and the actual measured output. Because this alters the original transfer function, we would need to construct a new transfer function for the whole system, call it G. When we insert the values for O and I and let things cancel out, we are left with the closed-loop transfer function of G. Any change in the output due to the disturbance will initiate a balancing act due to the regulator. Such is the case of the thermostat or the steam engine governor. If the regulation is determinate, the system started from a given state will follow a unique trajectory, but if it is Markovian, then there is no unique trajectory, so the system will exhibit a hunt-and-stick approach as it runs towards a state of equilibrium. Let's now apply some of the ideas studied here to a simple example of a regulatory system. The steam engine governor. It is a continuous and deterministic dynamical system consisting of two balls attached to a rod and rotating about with a certain angular momentum. The balls are connected to the engine so that they control the quantity of steam input and thus the speed of the engine. If the engine speeds up, the centrifugal force causes the balls to gain momentum and rise, closing the intake valve and subsequently decreasing the speed of the engine. This causes the balls to then lose momentum and fall, opening the valve again and increasing the speed of the engine. Because of this back and forth, the governor can be modeled as a simple harmonic oscillator, similar to the mass on a spring from the first part, but with the two phase space variables being the angular position and momentum of the balls. The rate of change of the angular position is the angular momentum divided by the moment of inertia. The rate of change of the angular momentum is the torque, which in this case is minus kappa theta, where kappa is the restoring force constant due to gravity and theta is the displacement of the balls from equilibrium. The feedback is again negative. By clever design of the governor, a damping factor can be introduced, which is typically provided by the friction in the bearings and the resistance of the steam valve. This damping factor ensures that the governor reaches a stable equilibrium point without excessive oscillations, effectively maintaining homeostasis in the engine speed. While the steam engine governor regulates a single parameter, living organisms must maintain homeostasis across a vast array of interconnected variables, from temperature and pH to nutrient levels and metabolic rates. The number of parameters involved in the regulation of a living organism is orders of magnitude greater than that of the steam engine governor, with the human body alone estimated to have around 37 trillion cells, each containing numerous regulatory pathways and feedback loops. In comparison, even our most advanced artificial neural networks, with billions of parameters, pale in complexity when compared to the intricate web of self-regulating systems found in nature. The steam engine governor, with its handful of components, serves as a simple yet profound starting point for understanding the fundamental principles of homeostasis and adaptation that underlie the complexity and resilience of life itself.